Welcome everyone to this new session of the REMAR seminars. And in this case, we have the chance to, or the opportunity to listen to Gabriel Machado. He's a researcher and PhD candidate from the Federal University of Rio de Janeiro in Brazil, from the GERO COPE group, research group. And he's going to present today for us a talk entitled Computational Modeling Applied to Offshore Renewable Energies, an overview. And I think it is a topic that fits perfectly with the topics we are dealing with in our network. And I'm completely sure that we are going to learn a lot based on his experience and his excellent way of presenting that he demonstrated some of the times. So, Gabriel, thank you for preparing this seminar for us, and I leave you the floor.
Okay, thank you, Professor Lafosse. I'd like to thank you for the opportunity and to present a little bit about my work, just a small part of everything we have in offshore renewable energies. So this is a presentation about an overview about the computational modeling applied to the offshore renewable energies. So to start, I would like to present you the group that I'm part of. It's GERO group, it's Ocean Renewable Energy Group. This picture was taken in the last seminar, last conference that we prepared. It was in Rio. Many of you was here in Rio, so this was a small part of our group. So it's a very large group. We have different countries, many different peoples for a lot of different areas. So about us, our research focus is in ocean renewable energies with many different topics in related to this theme. So we are specialized in numerical modeling, computational simulations, experimental tests that we have developing for the next month. Our focus is in energy conversion, so we have to think about the energy conversion in offshore marine renewable. About a little bit about the research lines, we have many different research lines focusing different areas. One of them it's about the floating analysis of the floating platforms for large scale offshore wind turbines, CFD. We have some people working with CFD too. We have some people working in structural analysis for these large scaling floating wind turbines. We have some projects in hydrogen production, design analysis of the wave energy converters, especially in the wave energy converters. We have also the projects with OTEC, Ocean Thermal Energy Conversion Systems, that explore the different regions of our planet to see which one is best for put this kind of systems. We have to think them also about the planning and design, the hybrid tests. So this is a little bit about the experimental part. Digital twin, we have also people that works with digital twin too. The hybrid platform with floating solar farms. We have projects especially in this part of solar floating platforms. And we also have this small part here that is the projects focus on the decarbonization of oil and gas activities. So to start, I would like to show you a little bit about the floating offshore platforms, how we categorize different types. We have mainly 4 different types of floating platforms. The first one is the spar one, that is slender, deep draft floating structure that is mainly stabilized by the ballast, low ballast here. So this kind of platform, it's located here. So we have this triangle that shows us the 3 different main kinds of stabilization that we have. So the first one is this one that is the ballast stabilized. So this platform, it's 100% connected to this part here that is 100% ballast stabilized. So that's why it's a slender, very big, very long tube that is mainly stabilized by the deep ballast located here in the platform. The second one is the barge one. We have different methodology here. The stabilization of this platform is related to the large water plane area, so it is located here in this another point of the triangle. So we have very big water plane area. So this way we can stabilize through the buoyancy of the platform. So we have a totally different approach of the SPAR one. And we also have the semi-submersible one, that is the most common one, that is located between these two concepts. So it's located here. It's a little bit stabilized by the ballast and a little bit stabilized by the water plane area. So it's in the middle of these two concepts here. And we have the third one, that is the TLP, the tension leg platform, that is naturally it's unstable, but it's stabilized by the mooring system. So we have the platform that is naturally unstable, and we put very strong mooring systems to stabilize the platform via this this concept here. So this way we have, of course, we have mixed these concepts into different kinds of platforms, but these four ones, the main four types of the platform. And we also have the different types of mooring systems, that is the catenary system and the taut mooring system. The taut mooring is the one that is the tension leg that is stabilized via mooring system. A little bit about the wave energy converters. We have mainly three types of wave energy converters. We have the oscillating water column. That is, we have a system that has two parts. One, it's inside water that has a small part here that is a column of water, and we have a little part here that is the air chamber. So when you have the waves oscillates this column of water here inside. When we have this oscillation here, we the air inside the air chamber got pressure and generates the airflow through this this air chamber. So when the water goes up, it pressurizes the air, so the air goes off. When the oscillating here goes down, depressure the air chamber, so the air goes inside. So this way we have this water here that oscillates in upward and downward direction, generates this airflow here inside the oscillating water column. And this airflow drives a turbine here that can be Wells turbine or B radial impulse turbine, many different turbines here. We also have the point absorber type, the buoy here, that is mainly a buoy that oscillates with the waves, and this way it's connected to a power takeoff system. That is the mechanism, the device that converts these oscillations in the buoy into the actual power to deliver to the system. And we have the overtopping device that is a little bit less common. That is a device that it's mainly fixed here, and when you have the waves run up this ramp here and is located here in this tank. And since we have the difference altitude here with the tank and the water line here, we have the storage tank is above the sea, so we have this flux here, this flux of water here that is generates also power that drives another turbine here. The difference is this turbine here is inside water, and this turbine here is an air turbine, so it's outside the water, don't have any contact with the seawater. And this one is inside the water, so the difference between these two levels drives this turbine. And here I brought these two examples in the world that we have. We have this Mutriku power production here, that is an OWC that I think is the most famous one, is located in Basque Country. And we have this other type here that is in Pecém here in Brazil, that was developed by my advisor, Professor Jean, and we have here in Brazil that it still works, and it's a very innovative concept too. A little bit about the hybrid concepts. When we think about hybrid concepts, we have to mix two different technologies to produce power. So we have the primary one, that is the wind turbine here, and we mix this wind turbine with different ways to generate power. I brought here the mixing about the wind power and the wave power, but we can have solar, we can have different concepts too. I brought these concepts here because it's the most famous and most conventional ones. We have mainly almost all of this is semi-submersible with different technologies. We have this point absorber here, different types of point absorbers. This way is a torus shape point absorber. So these three is all about the buoy too. So different kinds of buoy, but always all of these three buoys, point absorbers. We have this in Spain that is oscillating water column mixed with the semi-submersible. We have this one that it was one of the primary ones that mix with the surge movement here. So we have the surge movement of the platform. We generate powers together with the wind turbine, and we have this concept here that is the most the one that I study when I spend my time in Italy, my internship in Italy. That is a spar type wind turbine with 3 oscillating water columns here. The main focus in this work is to help to stabilize the platform. So the main focus here is not just about gathering power; it's also about the stabilized of the whole platform. So now the real topic of this seminar is about the methodology that we use to simulate these kinds of platform. We have to think that is when we want more accuracy in the test, in the simulations, we will get more cost, computational cost. So when we get more accuracy, more fidelity, we have more computational cost. It's always like this. So if you have the simple methodologies, linear frequency domain models, we have a very low cost of computational low cost, but we have not too much accuracy. So we have these kinds of linear frequency domain that is based on the potential flow theory with Morrison elements. We have the BANG, the boundary element method to simulate the aero part. And we can improve this methodology a little bit when you got to the time domain models. So we have partially or completely nonlinear coupled time domain models that is based on potential flow theory and Morrison elements. We can combine these two together, and we have in the aero part the boundary element methods and the free vortex wave to simulate these time domain models more accurate than the other one. And we also have the most advanced simulation method, that is the CFD, the computational fluid dynamics, that is more cost than the other ones, but it's much more accurate. That is different types of CFD, less runs, different kinds of simulation that can be simulating the aerodynamics part, the hydrodynamics, and the structural part. And also we have the physical test, that is the most reliable one, that we have the physical platform there, that we can see how is the movement, how is the behavior of the platform. And all of this, we have more accuracy, but we have more cost too. And here is just a picture to show you how we can think about a coupled model. When we have a coupled model, it means that we have different types of simulations occurring at the same time. So we have the aerodynamic part, We have, in my case here, the thermodynamic part that simulates the OWC. We have the hydrodynamics, we have the mooring systems. All of this is simulating together in each time step. So we have one point of the simulation that calculates all the aerodynamics, passing through the hydrodynamics and the thermodynamics, all of this coupled together in one simulation that takes into account all of these blocks here. And here I just put the dynamics, the simulation parameters that we can have, for example, the wind conditions, the wave conditions, in general, the environmental conditions, and the simulation parameters, which time step you want, how long you want the simulation, and stuff like that. So just to summarize, when you have coupled simulation, we have this different methodology. We can have wind, we can have waves, we can have current. All of this is coupled together into one unique model to simulate all of this together. A little bit the computational, the coupled numerical model steps. We have to think about how we create this type of method, how we create this type of modeling. So first we have to create the geometry and the structural modeling. So we can use different kinds of software to model this, conventional CAD, for example, SolidWorks, Rhinoceros, AutoCAD. We have to think about which concept we want to simulate, how is the structural design of the concept that we have. So from this part here, we get different parameters. We have the geometry, we have the mass properties, and we have the inertia. All of these can be calculated in these softwares, and it will be passed through the frequency domain model. So the inputs of the outputs of one is the inputs of the other one. So we have the mass, the position of the center of gravity, the inertias, and the geometry mesh inputted into the frequency domain model. When you have this frequency domain, we can use also different softwares that calculates the hydrodynamic radiation and the diffraction problem. That is the Aqua Ansys, Vomit, Captain, HydroD, OrcaWave. All of these softwares calculates the frequency domain analysis of the platforms. We can have the outputs from these types of model. We can have the added mass, the wave drift force, the hydrostatic stiffness, other coefficients of the platforms, radiation damping, and all of this. It's very important because when we want to pass to a time domain model, we have to have this as a parameter, as an input to our time domain model. So we calculate this, we can have coupled two different softwares here. For example, we can take the results from ANSYS and calculate in Waxing or OpenFast, that is my case, or we can use the ANSYS Aqua to calculate the time domain into the same software, but different tools inside the software. So in the time domain model is a little bit more complex because we are simulating the real time. So it's not the frequency, it's the real time. We have different parameters that is calculating through all the time step. And we also can have different softwares here, WaxSim, OrcaFlex, SIM, OpenFast. All of these softwares take these parameters in the frequency domain and calculates all the outputs that we can have. This means we can have the motions, the 6 degrees of freedom motions, surge, sway, heave, roll, pitch, and yaw. We can have the power, the wind power, the wave power, the solar. We have the accelerations, velocity, and the structural loads. All of this is very important when we have to design our model, our concept. So these models can be uncoupled or coupled models. So when you have the coupled model, it takes into account the aero part, the hydro part, the servo part, that is the controller, the structure, and the mooring lines all together in the same model. So this is the basics of the coupled numerical modeling into offshore systems. So to talk a little bit more about each of these models, the first one is the structural model. when you want to create the structural model, we have to create the whole system, the whole platform that we want to simulate in one of the softwares. For example, here I use SolidWorks to model this platform that is concept created by our group, GERO. And we have to model the whole platform with the internal structural configuration. We can put the material properties to see which the correct mass of the platform. So this way we can have also the structural model, we can have the loads, and we have to create all of these separate. For example, I can create the whole platform with one material, and we can create the ballast model separately. For example, here I create the ballast into water in the platform in concrete, for example. So we can create these different materials to get the correct value of the mass, the COGs, the inertias. And we also have to create the tower model. We have to have all the positions, the mass for the tower to correctly implement this in this model. So here I showed you very slow, very small picture of the hybrid system that I work. Is the conventional platform that is just the wind turbine platform here, combined with the wave energy converters. So we have here one model that takes into account one OWC inside the columns, and another concept that takes into account the OWC external to the columns here. So here I have three different materials. So we have the platform that is the concrete, we have the seawater here that is the oscillating water column, and we have the chamber here that is the steel. So when we put all of this together, we can get the global mass estimation in the correct form, the COG, the inertias, and the geometry in a correct way. We don't need to have to estimate nothing. We have the correct values of all of this. A little bit about the hydrodynamics. When you have different methodologies, we have the low fidelity model, that is the first one that I mentioned before, that is the frequency domain model. We solve this equation here, that is based on the frequency of the waves. So the low fidelity model takes into account this. We have to solve all of the software solve this equation mainly here. And we have the medium fidelity that is solve this Laplace equation that is based on Navier-Stokes equation, but we have to consider that the fluid is inviscid. This means without viscosity, that is the incompressional and irrotational. So when we consider the Navier-Stokes equations and we put these parameters here, we get the Laplace equation, and we have to solve this Laplace equation to solve the time domain model. This equation goes into this another one that is three different equations here, that when you solve this, we get this famous equation here that is the Cummings equation. That means this one here. So we have the potential theory, that is this equation here that takes into account the incident waves, the diffraction waves, and the radiation waves. When we solve this equation, we have the frequency domain problem solved. This means the aqua, for example, when we want to solve the diffraction radiation problem, it solves this equation here, that is these different incident waves, diffraction waves, and radiation waves. And when we goes to the time domain, we have the hydrodynamics in time domain, that is the Cummings equation, that is the basics of the coupled model. This means we have the mass properties here, and it's based on the second law of Newton, that is mass plus times acceleration, we get the forces. So this takes into account all the forces that we have in the system. So we have the extensional force, the nonlinear viscous force, for example, the Morrison elements. We have the PTO system, that the force that applied into the wave energy converter. We have the mooring system that applies the force, and we have the aero forces that is the basics on the wind turbine. So when you solve all of these together, we take into account all of these forces, we can have the coupled model into the whole time domain. So a little bit about the forces. When you have the viscous force, for example, we have to think about the linear damping coefficient and the quadratic damping coefficients. And we can also have, or depends of the model, we can have the Morrison elements to take into account the Morrison elements viscous forces too. So when we have the fully coupled model, we can put this force here to considering these Morrison elements here. And when we have the PTO force, for example, we can have one example here is we can have, for example, the pressure force, that is the force that the oscillating water column do in the platform, and we have this pressure force that is because of the air is pressurized into the air into the air chamber of the oscillating water column. And we also have the viscous force that is because of the PTO too. So we have the water that oscillates into the chamber. So we have this viscous force that have to take into account too. When we get the PTO systems, this is the mainly this just 3 examples of how we have this PTO system, how we simulate this PTO system. This the power takeoff systems. This is the device that is the responsible for generates power. This device, it get the movements of the buoy of the turbine and generates power from this. So we have the main one is the hydraulic PTO system. For example, here we have a float, a buoy that oscillates here, and we have a piston, and this movement passes through a very long system, and at the end generates power in this mainly system that is more common in the buoys, the point absorber. We can also have the direct drive that is a spar and a floater here, that is when we oscillate the magnets, it's coupled to the spar and with a coil inside, and we change this magnet field here, we generate power through this different methodology here. And in the OWC concept, we can also have the air turbine. We can have the wells or the impulse turbine here. That is when we have the water oscillating, we have this that flows, that airflow that drives this air turbine here, generating power. When we talk a little bit about the aerodynamics, we have 3 different models. That is the blade element momentum. That is the most simple one. That is more popular method for evaluating the aerodynamics in the wind turbines. We can have the free vortex wave that takes into account the wave effects of the blades. It's more realistic than the blade element momentum, but it's more cost. And we have the most advanced one, that is the computational fluid dynamics, the CFD, that is based on the Navier-Stokes equation. We have DNS, LESS, and RANS. The difference between them, these 3, is one of them, we have the model to simulate the turbulent here, the turbulent field here. We can have different approaches. One is we simulate some turbulent field, and we can calculate and simulate. The difference between between these 3 is one of these calculates all the turbulent vortex. One simulate and calculate, and the other one just simulate the vortex in the turbulent field. So that's why we have 3 different methodologies for CFD. A little bit about the blade element momentum. We have the blades here. We can calculate the lift and drag forces. That is, I won't go much more into the equations here, but just to explain that we have mainly 4 different equations: the lift and drag forces here, and the thrust and torque equations here. That is, we can have this all calculated into the tables that we can use in a linear model, or we can calculate this for each time step that is a little bit more complex and a little bit more costly. So we can have, we can calculate all of these for each time step to have, to have the more accuracy in our model. And about the CFD, we have, as I mentioned before, the Reynolds average Navier-Stokes that models all the turbulent scales, that all the vortex here. So this one models all the turbulent scales. The large edge simulation solves the larger turbulence scale and model the small ones. And the DNS solves all the turbulent scales. This means when you're solving the turbulent scales, it's more complex, more costly, and more accurate. So we have these 3 different methodologies to solve these different scales of turbulence in the system. About the mooring system, we can have finally the last one is the mooring forces that we have. It's based on, we can divide the mooring line into different small parts to calculate all the stiffness, the terms, and the weight in different small parts to have all one big system. So when we have this, we have one big equation that all of these terms is other equations. So we have the axial stiffness, the viscous term, and the buoyant weight of each part of this line. And we also have the drag force, the inertial force, and the reaction force for each of these small parts in the lines. When we consider one line, if you consider more lines, each line will have to calculate all of these equations. So we have a lot of different equations, so that's why it's more costly when we compare the fully coupled model when we compare with a non-coupled model. We have to consider all of this for each time step. So if we consider, for example, a time step for 0.01 seconds, we have to calculate for each 0.01 seconds all of these equations. So it's a very costly models. Just to exemplify a little bit about the results that we can have for different methodologies, for different models. When you solve the hydrostatic about our platform, we can have the draft of each platform, the position of the COG and the COB, the center of buoyancy. We can have the metacentric height of each platform. This is just an example that I put here just to show what kind of results we can expect for each step of our simulation. And we can have also the inertias and the total mass of the whole system, considering the platform, considering the tower, the blades, the nacelle, the rotor, everything considered here for the total mass of the platform. When you got to the frequency domain, the kinds of results that we have is the hydrostatic, as I showed before. We have the analytical natural periods of the platform. We have the added mass, the radiation damp, and the RAOs of the whole system. So I just put here as an example how we can see these kinds of results. That is how is the system, the response of the system through the period or through the frequencies of the waves. So we have the response amplitude operators of the system here. This all is solved in the frequency domain model. When you got to the time domain model, the things get more interesting, because we have a lot of different kinds of results. We have we can calculate a lot of different things. We can have the displacements of all the system. So if you consider, for example, this system here, we have different bodies. This means we have one body that is the platform with the tower and the wind turbine, and we have this oscillating water column here that it's another body, different body, and we have these other two here. One is in front of the other one here. That is four different bodies that can have to calculate all of these equations for each body, and how one influence the other one. So all of this is calculated into the model, and we can have the displacements of each body, we have the velocity, we have the acceleration, and we also can calculate the wind power, the wave energy converter power, tower loads, blade loads, hydro forces, mooring forces, blade pitch. This means all of these results we can get from the time domain model. Here I just put a figure about the free decay test that we can have. So when this means that we can have these kinds of results when you consider to see how is the damping of each platform of our system, how is the behavior of our system when you have the free decay tests. And we also have the more beautiful videos that we can have. For example, let me put again, we can see how is the behavior, we can actually see how is the behavior of our system instead of just see some graphics and some parameters. And to finally, the experimental tests, we can have different methodologies, but this is a little bit complex because when you have when we want to experimental the system, we have to think about the numerical model and the physical model, because when we consider the hydrodynamics and the hydrodynamics and the aerodynamics, it's different scales. So when we consider the aerodynamic model, we have to consider the Reynolds scale, and we have the hydrodynamic, we have to consider the fluid scale. So these two scales are not fully compatible. So we have to think if we have the aerodynamics in the numerical model and the hydrodynamics in the physical model, or the opposite, the aerodynamic in the physical model and the hydrodynamics in the numerical model, because when you have this, we have to separate here into the simulation part and the wave tank part. If we have this first one, we have the simulation considering the aerodynamic forces, the aerodynamic part, and the wave tank doing the actual experimental part of the platform model. So when we consider this, we have to consider the scales parameter here to match all of these systems. And we can also have the hybrid tests. That means we have one platform here with the drones here. So we have the simulation, this part here. We have the simulation of all the aerodynamics part. We get the loads, the forces, the moments passing through these drones here that simulates that behavior of the blades. And we also can have the opposite. We have the actual blades here, the actual wind turbine here, and we have a platform here that simulates the displacements, the movements of the platform. So we have these two different methodologies to simulate this. And the most advanced one is the distributed tests that we have. Two different laboratories with simultaneous physical representation. So we have one that is the hydrodynamic laboratory that simulates the hydrodynamic part, and we have the other laboratory here that simulates the aerodynamic part. So we have these two tests occurring at the same time in a real-time communication and synchronization. So when we have this physical tests in these two approaches, in the hydrodynamic and the aerodynamic. So when we have this, we have the most advanced method to simulate, to experimental of these kinds of platform. So, but this is a little bit difficult. It's very new methodology, so we're still planning, we're still thinking about this. I think that's it. I don't know if I goes too high, too fast, but I think that's it.
It was very good, Gabriel. Thank you very much.
Thank you so much.
Thank you for this very detailed and illustrative presentation of the work. And I think we have some time now for a discussion. This is the part I like most. This part of the discussion where people can participate and make questions and give you some suggestions and things like that. So I would like to open the floor for questions from the audience. So please, whoever like to participate, please raise your hand. Antonio, please.
Yeah, thank you, Gabriel. It was very nice presentation. My question or comment would be, because, well, you present all the different subsystems or submodels that we need to be integrated, and for each one you can have different levels of detail, right, in the model. From lookup tables to more dynamic, so on. So for me, the most interesting discussion, and maybe for the rest, is how does the uncertainty on each of the individual models propagates into the overall uncertainty of the overall results, because maybe the wrong model selection on one of the subsystems kind of cascades independently of the more detailed model. So can you say something about it, about how this level of modeling detail in each subsystem influence the overall model uncertainty?
Yeah, this is a very interesting commentary, very interesting topic. Is part of my next steps of my PhD is which one is the best module here to got more into detail. For example, if we have a CFD analysis in aerodynamics, but we have a linear frequency domain in hydrodynamics, how this propagates into each other, which one is the most we have to detail more, is part of my next steps. I didn't did this yet, but it's in my mind to see which one we have to get more into detail, to see which one is propagates more into the whole system. But it's very interesting topic.
Thanks, Gabriel. And maybe interesting to mention also which level we are happy with, right? Because maybe for what we need, we are not necessarily to certain scale. And also with the experiments, right? Because also in the experiments, there's a level of uncertainty. So where is the balance?
But when you have more accuracy, you have more cost. So we have to balance all of this.
Indeed. But thanks, Gabriel.
Thank you.
Some other questions from people. Meanwhile, I would like just that we are here considering this cost and accuracy balance. When you mean cost, are you considering computation time or the cost related to the softwares involved?
Yeah, until here, this part here is more computational costs. When you have physical tests, we have real money costs, because we have to build all the laboratories, we have to build all the models. But when you got through linear to non-linear to the CFD, we have more time consuming. We have more computational costs in how long the simulation takes, or how good our computer have to be to simulate this.
But in the first part you mentioned is more related to the, let's say, the how expensive is the software involved, right?
Yeah.
Okay. So I have meanwhile some other people is preparing some questions. I have a few of them prepared here. Regarding you mentioned the possibility to simulate or to analyze through numerical computation the different parts of the system. And in the methodology, you presented almost every system, but I would like to focus on the PTOs because you also provided some different types of PTOs depending on the system. What level of accuracy, by using the same tools you presented in the methodology, what level of accuracy can you provide for this type of system, for this part, for the PTO? Because it looks
Yeah.
like in a different, let's say, dimension.
Yeah, here I brought these three examples because I work mainly with the waxing software. So this is the three different types that I can simulate very fast. These first two, hydraulic and direct drive, it's already in the website. So everybody that wants that can go there and see how this works, how this actual can be implemented in the system. I don't know if I understand very well your question, but the first one is mainly with the buoys, the point absorber. These two actually, the direct drive is mainly with the point absorber type, and the air turbine is more in the ocean oscillating water column devices because it's the air turbine, so we have to take into account this airflow.
Well, my question was more mainly focused on in the idea that you provided very accurate models for the mechanical part and the structures and everything. But once you move into the PTO systems, and especially if you are considering WEXIM, that uses a quite, let's say, general model of the PTOs, uh, do you consider is it enough for an evaluation of your system?
Yeah,
Because
since
it seems you put like a lot of accuracy in some parts, but
yeah,
not in the other. How
yeah.
important is the PTO in the evaluation of the whole system? That
Yeah,
was mainly my question.
yeah, okay, now I understand. Since the waxing is open source, it's open for you to evaluate all of if you want. For example, you take this general model here and you can put more details since you have the open source. For example, in my case, I take this model with the guys in Italy, and that considers a very accurate model for the air turbine. So takes into account the compressibility of the air, the mechanics, the air turbine mechanics, the thermodynamics into the air chamber. So we can put the more fidelity since we need. For example, we take this model, the general model, and we can put more details since we want. In my case, I didn't focus on these two, hydraulic and direct drive, because my work is more related to the OWCs. So I took this model from the guys in Italy and put details as I needed.
Okay.
I consider the air compressibility, the how is my impulse air turbine works, the parameters, and I put some efforts in the where I need. Basically, is this.
Okay, good. Some questions? Okay, let's.
I do
Some
have a
other.
question.
Yes, Christopher.
Yes, sorry that I cannot use my camera right now, but I wanted to ask you a question, Gabriel. So normally when we model the PTOs, we use like linear models, and we use, let's say, this model of the PTO, let's say, to predict the behavior of the system. and to use it in the control strategy that we implemented in the system. So, do you have any insight about how this linear approach to model the PTO actually, let's say, induces error in the prediction, and so how accurate are they, and how useful? Because we are just starting, let's say, doing research in this field, and we are just simply using a linear model for the PTO. But I'm always very curious about how good is this, or if it is good enough to make good predictions about the behavior of the system and the accuracy of the validation with the experimental results. So I would like to know something about that.
Yeah, in the literature, the most common one is the linear models for the PTO system, but this depends a lot. Depends of the system that you have, depends of the concept that you have for the wave energy converter. For example, if you consider OWC, that is very they have many different approaches into the same system. For example, you have the air chamber, we have the air turbine. If you consider the linear model for all of these, cannot be so accurate that you want. So you have to consider a non-linear approach. But if you have a buoy, you might also consider a linear approach, because this is something more simple to implement, and we can put the effort in another part. And we can consider, for example, some control parameters into the system, but still be linear. So this depends a lot of which kind of system you have, which kinds of concept you have, if the linear can be a very good estimation or not.
I see. I understand. Yeah. I completely understand your point here. So actually, our system is just a WEC, and the PTO is a direct linear actuator. So I think so far it will be good enough, but we still have to run the experiments and see which discrepancies we find between the modeling and the actual experimental data. So I was just curious about if the model it will be good enough, or if we will need to work a little bit more on it. But I do appreciate a lot of your answer. Thank you very much for your presentation. Very nice work.
Thank you, Christopher.
Okay, who's next? Not so far. Meanwhile, I have another question, and this is regarding one of your last slides, Gabriel, when you were talking about this distributed test, which is something it really is quite attractive to me, because I have tried to organize something like that recently. So I just wanted to you to say a few things more. Is this something based on something you already know that has been working between several or some laboratories, or is just an idea?
Yeah, I don't know how much I can tell about this. I don't know if I can talk so much into detail this, but it's a concept that we are thinking about for the next years. We still have some projects, some ideas to build this, but it's in our plans. I don't know how much I can tell you about this, because it's a project that's still in process. But we are thinking. It's already not just a methodology anymore. It's real. Like, we can construct this. We can think about two different laboratories, physical laboratories, and put these together, synchronize these two different laboratories together.
Okay. I think we are going to talk something about this in the near future, because I have to tell you that there are some initiatives already been done at least in Europe, and I have some references I can share with you, and also I have been doing some checks with people involved in real-time communication, in order to ensure what or to check what is necessary to ensure the proper synchronization. And I think this is a good opportunity, especially in our environment, which is a set of small labs with, I think, quite important capabilities, but very spread out
Yeah.
geographically. So
Yeah.
that this would be, in particular, a good opportunity to connect our capabilities and to increase the impact in a quite bigger result.
Yeah, yeah. This
So,
is I think
yeah,
this is very difficult to synchronize everything to put this to work efficiently. But yeah, it's a possibility in the future because we already have some plans. But it's of course a very
uh,
challenging problem that we have to face it.
okay, yeah. So again, I put an eye on this, and I invite some of the people who maybe has some previous, I don't know if information or at least it results interest in this topic, because I think it's one of the things we should explore in the near future
Yeah, of
regarding
course.
our, insist, regarding the network and the different laboratories involved.
Yeah, of course.
So
Yes.
thank you for taking this out, because I'm glad somebody
Yeah.
else is looking at this.
Yeah, very important topic
Mm.
and very advanced topic too.
It is indeed. Somebody else like to share some other questions, comments, ideas?
Hello, I have a question for
Yes,
Gabriel.
go ahead, Julian.
First of all, Gabriel, thank you for your presentation. This is very valuable for us that we're starting this world. And my questions were in the slide of frequency domain. I think it was like about the radiation damping. The first of all, the first question is this component of the dynamics radiation damping whole estimated by the hydrodynamic damping, or do you consider another like components as this radiation damping by the anchor system or by the soil? That's like the first
Yeah.
question. Okay, you
No,
can.
no. In this frequency domain model, we didn't consider the anchors yet. For these types of simulation, we consider the radiation damping, that is the platform that natural damping, for example. It's all calculated into the software. We give the inputs and it's automatic calculate. He solves the equations and get the radiation damping.
Okay, sure. And that was like the other question. Does it get like an estimation of the radiation damping, or it gives you like the dynamics of the systems, including this parameter?
Yeah, is the graphic is exactly like this one. We have the added mass, the radiation damping, the RAOs exactly like this. We have our frequency, our period. We can give a range of frequencies that we can have, and we have the behavior of the curve, the added mass, the radiation damping, and the RAOs, giving the period that we have. For example, in this case here, we have a 30 seconds period. We can get an RAO of this value here. We have the same for the radiation damping, all calculated into the system, into the software.
Okay, sure. So, well, that was it. Thank you very much for your answers.
Yeah, to calculate these RAOs, you have to consider this. We have the added mass and the radiation damping, and we take this into account to calculate the RAOs. So that's why this is the input for the time domain. So we have in the time domain these values taken into account to calculate each time step.
Okay, I got it.
Thank you, Julian, for the question, and Gabriel for the answer. Any other question from the audience? Okay. I think we can conclude here. Just first of all, to say thank you to Gabriel for preparing this very nice presentation for all of us. I think there are many important issues here. We have a reference for numerical computation of these systems, so we have somebody to ask in the network. And I would like to thank also all of you for attending and for the discussions. And I hope we can join together very soon in the next seminar.